So today's due now. Like I said, it's a review of what we did last week. So we talked about different types of measurements, significant figures, and scientific notation. Those are some of the main points from last week. What do we have for our answer for number one? Is the measurement 16.70 milliliters a length, volume, or mass? Yep, it's a volume. And the giveaway is milliliters, right? How many significant figures are in 16.70 milliliters? Good. 466. So this zero is measured. Okay. Now how do you write 16.70 milliliters in scientific notation? Yep, exactly. So those of you who are participating, you're definitely getting it. Just don't forget your units. And also don't forget this zero. Okay, so 1.670 times 10 to the first milliliters, because that zero is significant. So we want to make sure to keep it in there. All right, excellent. So we're going to get started with chapter 2, the metric system. That was a pretty long video. It's a kind of a big chapter. There's a lot of concepts, and a lot of students get hung up on the conversions. So I wanted to take time to make sure that we did several problems together to kind of make sure you get comfortable with the process. Before we get there, we're going to just quickly go over the quantities that we're talking about, the physical quantities, the basic units, and the symbols. So take a second and fill in this chart. It's pretty much exactly like the one from the chapter 2 lecture. So it had the physical quantities, the basic units that we're going to use in this class, and the symbols for those units. So jot this down in your notebook, fill it in. I'll give you a minute, and then I'll fill them in. This is a good reference for yourself if you don't already have this in your notebook. I'm going to start slowly filling this in. Just make sure that you have it right in your notebook. For the first row, the basic unit is meter. So that means we're talking about a length. And the symbol for that is an M. We talked about volume a little bit already in our do now. The basic unit is a liter. And the symbol is a capital L. Here we've only got the symbol as a G. You should know that that's for a gram. And then you work backwards to say, well, grams, that's a mass. And finally, time, the basic unit is the second, which is abbreviated as an S. So make sure you know those, especially as we move forward in the class And when we revisit doing calculations and stuff towards the end, you're gonna want to make sure that if something is asking for a mass, that you report it in units of mass like grams or kilograms. Likewise, if you have to report an answer as a volume, it should be some kind of liters. So it may seem a little silly now, but when we get towards the end of the course and your brain might be a little bit mushy, that's when this is going to come in handy. All right. Are there any questions on this so far? If not, tell me you're good. All right. Excellent. Now we're going to move on to probably one of the more difficult topics of the course. And I'm not saying that to scare you, but it's just to let you know that you need to spend a good amount of time with Chapter 2 if math was not your thing, or if chemistry was not your thing in high school, or if you've taken 103 before and you were like, mm-mm. So make sure that you spend time with this and that you practice. Don't forget about the prerequisite science skills, but make sure that you spend some time on Chapter 2 because there's a lot of math and problem solving involved. So I put this chart here that you should have seen in the video as well. All the prefixes that we're going to be dealing with are right here. The main ones that we're going to be dealing with in this class, because they're kind of the most relevant to the type of chemistry that we may be talking about, are kind of within these two black lines. So as big as a kilo, small as pico. Now I could give you a question on something bigger, but for the exam, you will get this whole chart. So you don't have to worry about trying to memorize it. I just want you to understand how it works. So here is the base unit. So let's do a solid example. Let's say that we're talking about meters. So here in the center is 1 meter. If we have 1 km, that means we have 1 kilometer. And over here, this number tells you what that really means in meters. So that means you have 1 times 10 to the third meters, or 1,000 meters. Now let's say I were to go down to milli. 1 millimeter. What that means is I have 1 times 10 to the minus third meters. Does everybody understand how this chart works? If you have questions about it, let me know. Okay. All right. So I just wanted to take a second to make sure everyone could read the chart before we move on. Cool. So let's do some practice. I want you to try number 1. Write a unit equation to describe centimeters and meters. And then we'll go through it and make sure that everybody's on the same page before we start doing number 2 and number 3. So try number 1, just number 1, and then we'll go from there. When you have an answer, you can put it in the chat. Otherwise, you can just say help. If you're like, don't get it, don't call on me. Okay. Usually this part is a little tricky. So let's do number 1 together. We have centimeters and we have meters. We have to choose, we're going to write one in reference to the other. So we can do it 2 ways. I'll show you both. Let's say that I have 1 centimeter. And I want to figure out what that means as the number of meters. Is centimeter bigger or smaller than a meter? Right, it's smaller. So if I'm taking centimeters and making it into meters, I'm going from a small value to a big value. If I have 1 centimeter, I'm going to go to my chart. Do not worry about this exponent here. You can, if you want, you're going to take this number, 1 times 10 to the second, okay, meters. But you're going to determine your exponent based on which direction you're going. You're going from something small, centimeters, to something big. So that means that you're going to have a negative exponent. Think about it like if you had a pizza. If I have a slice of pizza, but I want to talk about it in terms of whole pizzas, that number is going to be smaller. So if I have 1 slice, that's 1/8 of a pizza. So that's going to be our small to big. We're going to have a negative exponent. Does that make sense? Because we're going to do it another way, and I'm going to test you. So if it's still kind of shaky, you can say help. Okay. So let's talk about it in a different way. Let's say that I have 1 whole meter, and I'm trying to figure out how many centimeters that is. We already said that a centimeter is smaller than a meter. So in this case, we're trying to take something that's big and convert it into units that are smaller. So would you expect the number of centimeters in 1 meter to be bigger than 1 or smaller than 1? It should be bigger. It should be bigger. So when we're writing this down, we're going to have a positive exponent. So we're going to take 1 meter and it's going to become a number bigger than 1. So 1 meter is equal to, you look at the number on the chart, ignore the exponent, because we're figuring out the sign of the exponent by which direction we're going. We're going from a bigger unit to a smaller unit. So we're going to have a positive exponent because we're going to have a bigger number. We're going to have a number that's bigger than 1. There's more than 1 centimeter in 1 meter. For the other example, and let me change my colors here. Oops. we had 1 centimeter, which is small. So if we take a small centimeter and we want to figure out how many meters that is, then that's going to be a number that's less than 1, because 1 centimeter, that's not a whole meter. And that's why we have something that's less than 1, because remember, that's what 1 times 10 to the minus 2 is. It's 0.01. So 1 centimeter is 1/100th of a meter, whereas 1 meter is equal to 100 centimeters. That's what we're saying here. We're just using scientific notation. So you have to think about it in terms of, am I going from a bigger unit to a smaller unit, or a smaller unit to a bigger unit? I'm going to go to the next slide here, but it's the same thing. We're just going to keep working on it. Okay, so don't get afraid. So number 2 was kiloliters and liters. And number 3, we had nanograms and grams. So remember, if you're going from a small unit to a larger unit, so the example would be centimeters to meters, then you're going to have a positive exponent. If you're going from a large unit to a smaller unit, you're going to have a negative exponent. So let's walk through number 2 again, let's walk through number 2, and then I'll let you try number 3 on your own. So for number 2, we have kiloliters and liters. Let's say that we have 1 kiloliter, and we want to figure out how many liters there are. So you have to establish, okay, we're going to talk about kiloliters. If I have 1 kiloliter, how many liters do I have? Am I going from a small unit to a large unit, or a large to a small? And somebody's already got the answer, sort of. But let's go through it step by step so that you have a process. Are we going from small to big, or big to small? Let's wait for a couple more answers. We're going big to small. The reason we know that is because kilo is up here above the basic unit. So it makes the basic unit bigger. Okay. Because we know that we're going from big to small, that means when we say how many liters there are, it should be a number that's bigger than 1. So we're going to have a positive exponent. 1 kiloliter, somebody already put 1,000. That's right, it's equal to 1,000 liters, which is the same thing, if you were to write it in scientific notation, as 1 times 10 to the 3rd liters. So for number 3, I want you to try it and do the same process. Say I have 1 nanogram, and I want to figure out how many grams do I have. Figure out if you're going big to small or small to big, and then what your exponent should be. Are you looking for a number bigger than 1 or smaller than 1? And then try to write it out. So I'll give you a minute to do that. Uh-oh. Put it back. My bad, y'all. I realized I wrote it backwards, even though I said it right, I think. But just to be on the safe side, I'm going to say it again. Small unit to a larger unit, we are going to have an answer that is less than 1. So it's going to be a negative exponent. If you're going from a larger unit to a smaller unit, then you're going to have a number that's bigger than 1, and your exponent should be positive. So I apologize if I said it backwards. It's early morning for me too. Small to big, you're going to have a negative exponent. Big to small, you're going to have a positive exponent. Does anybody have an answer? How many grams are in 1 nanogram? If you don't have a number answer, you can tell me whether or not it should be bigger than 1 or smaller than 1. Let's just start there. All right. So we'll walk through the process, but it looks like some of y'all are getting it. A nanogram is small, okay? Smaller than a gram. So that means that we're going to have a negative exponent. And our answer is going to be less than 1. We go to the chart, we look for nano, and we write it in. We said our exponent is negative, and there's our units. Would you like to do another example, just to make sure that you get it? We're going to be doing this like problem solving wise, but okay. So let's add in another one. If I have 1 meter, how many picometers do I have? I'm going to throw in, we're going to do 2 more examples. So there's 1. All right. So 1 meter is definitely bigger than a picometer. So we're going from a bigger unit to a smaller unit. So our answer should have a positive exponent. It should be big. This one you can, again, literally read it off the chart. 1 meter is equal to, and you go say, okay, 1 times 10 to the 12th, and it should be positive. So that number you get from the chart, but whether or not it's a positive or negative exponent, you figure that out based on whether you're going from big to small or small to big. For number 5, we're going to stretch outside of the normal zone that we would be working in, and we're going to say a megasecond. If you have 1 megasecond, how many seconds is that? You're looking at milli. What we're looking at is mega. Capital M. Okay, so most of you who have put in an answer put in a positive exponent. But there's one person with a negative exponent. So let's go over it and see which one it is. So we have 1 megasecond, and we want to know how many seconds. Megasecond is pretty big, okay? It's above the basic unit in the chart, so that means it makes your basic unit bigger. And then we're trying to figure out how many seconds that is. So that's a smaller unit. We're going from big to small. So we should have a positive exponent. One megasecond is 1 times 10 to the 6th seconds. Now, if I asked it the other way, if I had 1 second, how many megaseconds do I have? Then we'd be going in the opposite direction. A second is smaller than a megasecond. So we would have a negative exponent if we were writing it the other way. Okay? So those are two unit equations that state the same relationship. Oops. Should be megaseconds. So there are always two unit equations that you can write. But the way that I write them, because I think it's the easiest, is if you have a pair, then I just say, okay, if I have one of the first one, how many of the second one do I have? So that's typically how I think about it. On the exam, you're going to need to be able to recognize unit equations. So I may ask you a multiple choice question that says, which one of these, which one of these unit equations describes the relationship between nanogram and gram? And I'll have, one answer that's right and others that aren't. I'm not going to try to be tricky, okay, and give you both. That's kind of mean. But you need to be able to recognize the relationship and say, okay, yeah, this is the one. And I'll give you exam reviews, so don't worry about that. You're not going to have to just hope that you can figure it out and hope that you'll, be able to recognize how to answer the questions I'm asking. I'm going to give you an exam review packet. So can we move on from here? We're going to be doing actual problems where we have to write out unit equations and stuff. But I wanted to at least make sure that we covered this in a little bit more detail together before we moved on. So are we more comfortable than we started? Let's start there. Okay, good. That's the right direction. So now we're going to do the easier part. You already have the unit equation. Now we need to write the unit factor. And remember that the unit factor looks like a fraction. So I'll do the first one. Let's say that we have our unit equation 1 centimeter is equal to 1 times 10 to the minus 2 meters. Looks familiar. I'm going to take that 1 centimeter and write it over 1 times 10 to the minus 2 meters. That's a unit factor. But remember, I can get 2 unit factors from each unit equation. All I have to do is flip the fraction. Give that a shot. This is the easier part. Write the 2 unit factors for this second problem here. 1 kiloliter is equal to 1 times 10 to the third liters. You can write it as 1,000 liters. That's easier to type in. If you have an answer, you can go ahead and put it in the chat. Or, just like before, you can say help. Yep, we're looking good. So you should have those 2 as your unit factors. So you're just taking that unit equation and writing it out as a fraction. You're literally replacing this equal sign with a slash. You're making it a fraction. So are we good on writing unit factors from unit equations? You're going to need to remember the terminology. So if I say write a unit equation, you need to know that I mean something like this. An equation has an equal sign. If I ask you to write 2 unit factors, then you need to know you're writing 2 fractions. So let me know if you're good on that or if you want to do some more practice. All right. So we're going to get to our first word problem. We're going to walk through this together. I'll ask you questions along the way, and we'll get to the answer together. Then I want you to try one on your own. Here we go. This is our first metric conversion problem. You're performing an experiment that requires you to measure 56 milligrams of sodium bicarbonate. Your balance reports mass in grams. How many grams of sodium bicarbonate do you need? Report your answer in scientific notation. The first thing that you want to do is rewrite the question. So simplify it and write it down. We have to measure 56 milligrams of something. And what we're trying to figure out is how many grams that is. So that's our question in a nutshell. Now we need to figure out a plan for it. That means we need to write out a unit equation and some unit factors to figure out how to get from milligrams to grams. So, milligram, is it bigger than a gram or smaller than a gram? Right, it's smaller. So we're going from small to big. Do we expect our answer to be bigger than 1 or smaller than 1? So the number of grams, right, it should be smaller. So that means that we should have a negative exponent. Now we're ready to write a unit equation. Unit equation, I abbreviate UE, okay? That's a unit equation. So if I have 1 milligram, how many grams do I have? If you don't have that chart, the prefix chart, in your notebook or like have it saved like as a PDF somewhere, I suggest you do, because when you do your chapter 2 check-in and when you do the Mastering Chemistry homework and quiz, you're absolutely going to need it. But tell me, how many grams are in 1 milligram? Milli. So milli, that's what you would see on your chart, okay? So make sure that you know the capital M is mega, the lowercase m is milli, okay? Because I think that's where you guys are getting the 6 from. We're talking about milli. But you're right with the exponent should be negative. So we should have 1 times 10 to the minus 3 grams, which is the same thing as saying 0.001 grams, okay? I just like to use scientific notation because you can't always, I don't want to write out 5 zeros. I don't want to write out 11 zeros. So I get in the habit of writing scientific notation so that it just comes naturally, okay? Now we need to write our unit factors. We're going to write two fractions. Those are our two unit factors. But now we have to make a decision because this isn't the end of the problem. I don't have a number of grams that I need to measure out. I don't know what the balance needs to say in order for me to know that I have 56 milligrams of sodium bicarb, which, by the way, is just baking soda. So I need to figure out which one of these two unit factors I need to use to actually get from milligrams to grams. I'm going to write out the actual equation that we're going to use in a different color. So we're starting out with milligrams, and we want to end up with some number of grams at the end of the day. For this math to work out, I need to cancel out the milligrams. Milligrams right now is on top. So I need to use the unit factor that has milligrams in the bottom and grams in the top. So which one is that? I'm going to label them. Am I going to use unit factor 1 or unit factor 2 to go from milligrams to grams? Exactly. So that's the question that you're going to have to ask yourself when you're doing these conversions. I've got these two unit factors. Which one of them is going to get me to the units I want? So you need to cancel out the ones you don't want and be left with the ones that you do. So we're going to fill in our numbers. And this is where you really need to pay attention. So even if you write the units correctly, if you write the wrong numbers, you're going to get the wrong answer. So be neat, be tidy, and follow the same method each time you solve the problem. Even if it's not my method. If you see something on YouTube or somebody else has been taught a different way and that makes more sense to you, absolutely fine. Whatever you do, just be consistent. Me teaching you is me teaching you how I learn and what makes the most sense to me and what I've seen be most successful with teaching other people. But that doesn't mean that you have to stick to it. Try it, and if it doesn't make sense to you, come to me because we can tweak it together, okay? So we filled in our unit factor. Now we need to do the math. So in your calculator, I want you to try this because I want you to get into the habit of using your calculator to enter scientific notation. So you're going to be multiplying 56 by 1 times 10 to the minus third. Try that and let me know what your calculator says. Yep. So your calculator is going to tell you 0.056. But remember, in our question, it says report your answer in scientific notation. So this is your calculator answer. But what's our actual answer going to be? We have to write it in scientific notation. Oh, you got a fraction. So that means that your calculator is in exact mode, and it needs to be an approximate. I don't know what type of calculator you have, but that setting needs to change. So you can Google the type of calculator that you have, and then put, like change mode from exact to approximate, and you should find like a video or something like that. You're welcome. So right, scientific notation, we're going to have 5.6 times 10 to the minus 2 grams. Okay. Your scale is actually going to say 0.056, but I want you to get in the habit of writing in scientific notation. So chances are, if you see a question like this, the answer will very likely be in scientific notation. And I will give you a heads up. If I put a question like this and say, report your answer in scientific notation, you may see both of these answers, and you need to tell me this one. So I'm no tricks. I'm giving you the keys to the kingdom. So if you pay attention and you take note, you should be all right. So when I ask for scientific notation and you don't give that to me, your answer is not correct. It is wrong. You may get partial credit, but it is still not fully correct. So how do we feel about that? How many of you, let me know. And you're like, oh, I think I can do it, or still a little shaky. Okay. Then I'm going to let y'all try one, and then we'll go over it, and then we'll take a short break. Because I'm looking at the rest of my breakfast right now, and it's just like, hey, girl, how you doing? And I'm like, I'm hungry. That's how I'm doing. So if y'all are hungry too, then you can take that few minutes after this problem to rectify the situation. So y'all can eat. I can't, because I'm being here. That's no bueno. No bueno. So help your girl out. Let's do this problem. I'll go over it, and then we'll take like a 5 or 7 minute break. When you're finished, just say ready, and then we'll go through the problem together. Oh, we got the answer already. I was trying to avoid that, but that's all right. You can go ahead and put your answers in, or just let me know that you're ready, and we can go over it. If you're stuck, you can let me know. If you're stuck, you can let me know. All right, so we got some answers. Let's start going over it. First thing you do, rewrite your question, simplify it. That's a lot of words. How many milliliters are in 1.82 liters of water? Report your answer in scientific notation. That's our question. Going from liters to milliliters, is that big to small or small to big? I like the abbreviation. You can do that. BTS or STB. I like that because that's a lot to type. So we are going from big to small. So should we expect a big number or a small number? It should be big, right? So when we're writing this, our unit equation, we're going to have a number that's bigger than 1. So our exponent should be positive when we're writing it in scientific notation. So let's say I have 1 liter. That's going to be equal to 1 times 10 to the third milliliters. Now I have these in my head because I've been doing this for a long time, quite literally half my life at this point. Reference the table. Make sure that you're getting the right number because you may have the right exponent, like it's positive or it's negative, but if you use the wrong number, let's say that you put a 6 instead of a 3, you're not going to get the right answer. You'll get partial credit because you did the process right, but the very final answer will be wrong. Now that we've got our unit equation, we can do our unit factors. Those are the things that look like fractions, and y'all were pretty solid on writing those out, so I'm not going to bug you to write it out in the chat. Now, we'll label them 1 and 2. Which one of these unit factors do we need to use to go from liters to milliliters? Are we using number 1 or number 2? Everybody, for the most part, is saying 2. Let's see if that works. Let's set up our problem. We need to cancel out the liters. So we're going to have liters in the bottom and milliliters at the top. And that happens to be how unit factor number 2 is set up. Milliliters at the top and liters at the bottom. So we're going to fill in the appropriate numbers. And do some math. Now, if you write it like this, where you have the unit factor in scientific notation, you don't even have to touch your calculator. 1.82 times 1 times 10 to the third. And we make sure that we cancel our units. Done. So several of you got that answer. So even if you didn't chime in, hopefully you were able to get the pieces along the way. And if you got stuck, you saw where you were stuck. This is a good time to take a short break. We're going to do 5 minutes, and then we'll get back to it because we've got another few of these conversion problems to do, and then a few other concepts that we need to touch on before the end of class. So it's about to be 9:12. Let's come back at 9:17. All right, y'all. It is 9:17, so we are going to get back to it. So we started with just doing the metric conversions. You need to use one unit equation, one unit factor, and that was it. Now we're going to step it up a little bit. We're going to do two metric conversions. So that means instead of just needing the one, we need two. You're going to need to be able to figure out when you need to just use one unit equation and when you need two. And that's what we're going to talk about in this example. So I'm going to go through this one, and then you'll have the opportunity to do one on your own. So hopefully y'all ain't still breaking and you're back with me. So how many nanoseconds are in 5.21 kiloseconds? Report your answer in scientific notation. As always, we start by rewriting the question. We have 5.21 kiloseconds, and we want to know how many nanoseconds is that. Here's the key to knowing when you need to do more than one unit equation and use more than one unit factor when you're figuring out your conversion. Both of these units have some kind of a prefix. It's not just kiloseconds to seconds or seconds to nanoseconds. We're going from kiloseconds to nanoseconds. We cannot write one unit equation for this. You can't jump from kiloseconds to nanoseconds. You can't do it. We have to use a go-between, and that go-between is going to be seconds. Our first unit equation is going to relate kiloseconds to seconds, and our second one is going to take those seconds and convert it to nanoseconds. This is why I preach the gospel of be neat, be tidy, and use the same method every time, because you can increase the number of unit factors you need without having to completely change how you approach the problem. As long as you label everything and you know what's going where, you should be good to go. So unit equation 1 is going to describe the first leg of the calculation that we have to do. And that is going from kiloseconds to seconds. Is kilosecond bigger or smaller than a second? It's bigger. So we're going from something that's big to something that's small. Do we expect our answer for that part, should it be bigger than 1 or less than 1? If I have 1 kilosecond, Is my number of seconds going to be bigger than 1 or smaller than 1? Yeah, it should be bigger. It should be a bigger number. So that means when we're writing our unit equation in scientific notation, that exponent should be positive. Using your chart, you can fill it in. So that's our first unit equation. So our unit factors for unit equation number 1, we're just going to make 2 fractions. So that's 1. Now we have to do that again. We're going to go from 1 second to some number of nanoseconds. Are we going big to small or small to big? Yeah, we're going big to small. So again, we're expecting the number of nanoseconds to be bigger than 1. So there should be a positive exponent. So there's our unit equation for that one. Now we have to write the unit factors. Are we good so far? Okay. We've got our unit equations, unit factors. Now we need to set up the problem. And this is the part where things can get a little bit tricky. So let's set up our problem. We're starting with 5.21 kiloseconds. What unit do I need to have on the bottom? And what unit do I need to have on the top? So you can tell me whether I'm using A or B. You can tell me what should be in the top, what should be in the bottom. Just share something that you know. Yeah. So to cancel, we're going to have kiloseconds in the bottom, which means seconds in the top. And we're going to use B. What about for the second one? Because we're not done yet. We still have this unit factor number 2. So are we going to be using A or B? Yeah, we're going to be using B because we want nanoseconds at the end, which means we need to be able to cancel out seconds. Go through and do your unit analysis before you actually touch your calculator. So the kiloseconds cancels and we're left with seconds. That was what we went through with unit equation number 1. Then we're going to take those seconds and convert them to nanoseconds. So our seconds cancel, and we're left with nanoseconds at the end. Now you can touch your calculator and figure out how many nanoseconds we have. And remember, you need to report your answer in scientific notation. So go ahead and do that. Put your answer in the chat when you're ready. Yeah, we're getting it. So you should get 5.21 times 10 to the 12th nanosecond. Yes. So is it trying to figure out which ones you need to use? So when you're figuring out which unit factor to use, what you're trying to do is cancel out one unit. In this case, we're starting with kiloseconds. And for the first one, we're trying to get rid of kiloseconds. So with math, you need to have one in the numerator or the top number, and one in the bottom, the denominator. We don't write numbers like this, but 5.21 kiloseconds, you can think of it as being over 1, okay? So when you multiply by seconds over kiloseconds, you're getting rid of those kiloseconds and you're left with seconds, okay? Does that help? You're welcome. Good. Are there any other questions? Because the next step is to have y'all try one on your own. So if you're ready, let me know. I'm ready. Otherwise, we can talk about this one a little bit more. The magic number is 3. Once I see at least 3 people say they're ready, that's what we're going to do. So here's another 2 metric conversion. An experiment requires 25 picograms of an enzyme. How many milligrams of enzyme do you need? Report your answer in scientific notation. So I'll start you off, but I want you to finish it. Your question, you have 25 picograms. How many milligrams is that? Remember, you're doing a two metric conversion. You don't see just the plain old grams. Both sides have a prefix. So you have to go from picograms to grams and grams to milligrams. So I'll give you maybe 3 minutes to get started on that. And then I'll jump in and we'll finish it out. So if you get an answer, you can go ahead and put it in the chat. Otherwise, just kind of keep working and chugging along, and we'll see if we come to the same conclusion. How are we doing? You can say help, more time, or give me an answer. Small going to big. You're taking a small unit and making it bigger. So it's going to be a negative exponent. You're going to have an answer that's smaller than 1. And I'll give you guys another couple of minutes and then we'll get started on it. If you think you have an answer, you can put it into the chat. I like what I'm seeing. If you haven't gotten there, if you haven't finished, don't worry. I'm going to get started in the interest of time. So we already said we've got to do this in 2 parts because both of these units, the one that we're given and the one that we're converting to, they both have a prefix. So there's no way to get from picograms to milligrams directly. We've got to go through grams. So for our first unit equation, if I have 1 picogram, how many grams do I have? We're going from picogram to gram, so that is small to big, and we're going to have a negative exponent. Using your chart, you should be able to figure out 1 picogram is equal to 1 times 10 to the minus 12 grams. And for our unit factors, you just write out the fractions. So that's the first unit equation and the first set of unit factors. Are we good so far? Alrighty. Now let's do the second one. This time we're going from grams to milligrams. So is that big to small or small to big? It's big to small. It will not always be like that. Okay. So see how sometimes it was big to small and then big to small, or it's small to big, now it's big to small. So there is no pattern to this. It's just you have to figure it out each time. Since we're going from a bigger unit to a smaller unit, we're going to expect a number that's bigger than 1. That means a positive exponent. So if I have 1 gram, use that chart. That means that I have 1 times 10 to the third milligrams. So for right now, I want you to write out both because it's just the practice of writing the unit factors and things like that. But you don't have to write out both of them if you think you can just figure out which one you need once we get to the exam. It will not always be the second one. That's just kind of what happened this time. So you always have to do that choice of which unit needs to be in the top and which one needs to be in the bottom. You're welcome. So those are our unit factors for the second part. I need some color in my life, so we're going to go for some blue. Let's write out the equation we're going to use. We're starting with 25 picograms. Now we need to choose A or B from our first set of unit factors. So which one am I using? Right. We need to get rid of the picograms, so they have to go on the bottom. Now, we need to get rid of grams and be left with milligrams. So we're going to, again, go with the second one. And when you put that into your calculator, and you write it in scientific notation, you should get this, 2.5 times 10 to the minus 8 milligrams. So I know a few people put in an answer. How many of you either got an answer or you were on the right road, like you had all the steps right leading up to the answer, you just didn't get a chance to finish? You can raise your hand or say me. Trying to get an idea of how many people were on the right track, and maybe if you had a little more time, you could have gotten it. Okay, there's a couple people. I hope there's more than that. Okay. Make sure you practice these. So I will post additional practice problems. You don't have to submit them for credit or anything like that. But between doing the chapter check-in, the mastering chemistry homework, and the working through some of those additional problems, you should be able to get these. So it should become kind of like clockwork. You just got to practice the method and get comfortable with it. All right. So now we're going to do one more problem type. I'm going to go through this one, and then we'll move on from this topic. So we have compound units, which is a little bit different from the metric conversions, or even the two metric conversions. We're going to have two unit factors, but in this case, we have two units to convert. So in this sample problem, the average low flow shower head flows 3 gallons of water per minute. What is the flow of water in liters per second? Now, one thing that you're going to need to do this problem, which I would provide with for you, is how to convert from gallons to liters. I'm not going to make you memorize that. But for homework's sake, you can look it up on the internet. But I'll tell you now that 1 gallon is approximately equal to 3.785 liters. So that's information that you would have to do this problem. So we're taking 3 gallons per minute, and we want to know what that is in liters per second. So we have to change the gallons to liters, and then we have to change the minutes to seconds. For our first unit equation, we're going to handle the gallons to liters. Now, I already gave you that unit equation because it's a conversion that you would have to look up. You can't get that from a chart, or at least from the chart that I gave you. So that part's already done. 1 gallon is equal to 3.785 liters. Now we write out our unit factors. So that one's simple. For the second part, we need to go from minutes to seconds. So if I have 1 minute, how many seconds do I have? This should be something that you shouldn't have to look up because you've been dealing with time all your life. Yeah, 1 minute is 60 seconds. So our unit factors for that are going to be 1 minute over 60 seconds and 60 seconds over 1 minute. Now we've got to set up our equation. We've got 3 gallons per minute. And in our first unit equation, we talked about how to convert gallons to liters. So what unit do I need to have at the top and the bottom? Tell me if I'm using A or B. Because we're getting rid of gallons first. Yeah. So we've got to get rid of those gallons. So liters on top, gallons on the bottom. Good. Now we've got to do the second one. We want to get rid of minutes. Minutes are in the bottom this time. So now thinking about that, do I need to use A or B if I'm trying to get rid of minutes? So we have a couple of people that say A. We got some B. This is why unit analysis is necessary. So let's try it with B, okay? Let's say that I put 60 seconds and 1 minute. And then, before I touch my calculator, I make sure that I do my unit analysis. So gallons cancel, and I'm left with liters. But my minutes, I can't cancel my minutes. I've got minutes on the bottom and minutes on the bottom. So I would get something funky like liter seconds over minutes squared or something like that. We don't want that. So let's see what it would be like if we had the other one. If I used A, I'd have minutes in the top and seconds in the bottom. So I'd get rid of my minutes and I'd have liters per second. That's why I go through and do the unit analysis. So does it make sense why we're choosing A this time instead of B? Let me know if you're good. Help, just let me know something. Okay. So go ahead and do the calculation and tell me what you get. You don't have to do it in scientific notation, but that's fine. So you want to make sure that you do all of the multiplication and division. That's why I wanted to do this as well. So to put this in your calculator, you're going to put 3 times 3.785 divided by 60, because that's what it means when you have something in the denominator. You're dividing. So when you do that, yeah, your calculator is going to tell you 0.18925. That's your calculator answer. But we know sig figs. And the only thing that we have in this problem is the 3 gallons per minute. There's only one sig fig here. So that means for our significant figures, and when we're putting units and everything, we can only have one significant figure. So that's 0.2 liters per second. Don't forget about sig figs. We haven't needed them because we've just been moving the decimal point around. That's all doing these metric conversions is doing. But when you're doing compound units, you do have to take into account sig figs because you're multiplying and dividing and doing all the things and changing units in a way to where you're not just moving the decimal point. So you're going to have to take sig figs into account. There will be practice. You will see a question like this on the exam. So just be ready. Everything that you've seen so far, you're going to see a metric conversion. You're going to see two metric conversions, the compound unit problem, and you're going to have to write some unit equations and unit factors. So if you need more help with that, that's fine. We can do that during office hours. You can hit me up. Let me know, hey, Dr. Hefner, struggle bus, get me off it, and we can do that. So sig figs will apply every time. It just depends on the problem. If you, so we only have one number to go by. And when we're going from US units to metric units, there's always going to be decimals. So in something like this, where gallons is US and we're trying to switch to metric, there's always going to be sig figs involved in that. Same thing if we're going from like miles per hour to kilometers per second or something like that. It's going to be the same deal. Good question. You're welcome. So we're going to switch gears. That, I think, is kind of the hardest part, is doing those different conversions. So now we've got 30 minutes to touch on everything else. That's usually how it works, but that's okay. We're going to cover percentages first. So we talked about what a percent is. We're talking about a part over a whole times 100%. And that gives you a percentage. This part over the whole kind of looks like a unit factor, doesn't it? The answer is yes, it does. So we can use a percentage as a unit factor to convert one thing to another. So I'll do this problem out and I'll ask for your input. And then just along the way, let me know, like, hey, that doesn't make sense. And then we can break it down a little bit better. So the Earth contains 4.70% iron. How much iron is in a 71-gram sample? The first step to problem solving is always distilling what is the question. We're looking for the number of grams of iron in a 71-gram sample. What do we know? We know that the sample is 4.70% iron. We can rewrite that as a part over a whole and make it look like a unit factor. Remember that a percentage is always out of 100%. So if I have 4.70 grams of iron, that's out of a total sample size of 100 grams. It's the same thing as saying 4.7 over 100 or 0.47, okay? So those are the other ways that you can represent a percent, okay? So does this part make sense to you? Let me know if this is okay. Taking the percentage and writing it out as a unit factor. because that's the hardest part of the problem. I know, it's been a long one, y'all. We got another 30 minutes, and then you can shake your brain out. So now we just have to set up some math. We've got a 71 gram sample, and we're going to use that unit factor to figure out how many grams of iron we have. So just like we can write this unit factor, 4.7 grams of iron over 100 grams of sample, you can also flip it. So that's just for your knowledge, because you may have a question where it says you have a sample that has this much iron. How many grams is the sample? But in this case, we know the size of the sample. So we're going to go with this first unit factor. So do that math and let me know what you get. Yes. And don't forget, in your calculator, this is what you're putting in. Don't forget to divide by 100, or else you will get a very strange answer. So that's what your calculator says. But we have to take into account significant figures. Yeah. The percentage has 3 sig figs. The sample only has 2 sig figs. So that's exactly right. We have to use 2 sig figs for our answer. So the fully correct answer is 3.3 grams of iron. Thumbs up or help? Let me know which one. And I hope everybody else is still with me. I know it's a long class. 2.5 hours is a long time. But we still got some stuff to cover. So we're going to move on from percentages and talk about volume. Okay. The key with volume is if you're converting from one unit to another, you need to make sure to use your unit factor 3 times. So I'll quickly do this example for you. I don't know if y'all even know what a Rubik's Cube is. It's a toy that's popular in the 80s. It's probably not really popular now. They try to keep coming out with new ones, but anyway, it's a cube, and its approximate volume is 185.2 centimeters cubed. What is the volume of the cube in meters cubed? So our question here is we have 185.2 centimeters cubed, and we're trying to convert that to meters cubed. Well, this looks like something that we have to write a unit equation for, because we can relate centimeters to meters. If I have 1 centimeter, am I going to have something, is the centimeter bigger or smaller than a meter? Yeah, centimeter is smaller than a meter. So we are going from small to big, which means our exponent is going to be negative because we're going to get a number that's smaller than 1. Then we need to write out our unit factor. So that was our unit equation. We need to write out our unit factors. So if we're trying to go from centimeters cubed to meters cubed, we need to multiply by whichever unit factor we choose 3 times. Because centimeters cubed is the same thing as saying centimeters times centimeters times centimeters, and we need to cancel them all out. We're trying to get rid of centimeters, so it needs to go on the bottom. And we're canceling out centimeters each time. So that we're left with meters cubed. Is everybody still with me? So we did the unit equation to relate centimeters to meters. We wrote out our unit factors just like we've been doing. We figured out which one to get from centimeters to meters. And now the key to solving these kinds of conversions with volume is that you need to use your unit factor 3 times. So when you do that, what do you get? The calculator should say something like that, 0.000185. If we were going to write this in scientific notation, so we're putting our decimal point here, 1, 2, 3, 4. So that would be the volume of the Rubik's Cube in meters cubed. Notice how the number is smaller than the number in cubic centimeters. It should be. So do that kind of a mental check. Now we've got density. Okay. We're almost home. So density, remember, is equal to mass divided by volume. For solids, that's going to look like grams per centimeter cubed. And for liquids, it's going to look like grams per milliliter. And gases are different still, grams per liter. So those are just the different units that you're going to need to recognize as densities. Okay. And these units on the bottom are the various units you can have for volume. Now, the question that we have here is incorporating what's called volume by displacement. So you have some water in a graduated cylinder. You take your solid sample and put it into the graduated cylinder, and the level rises. Makes sense? That level rising is called displacement. The difference between the initial reading and the final reading of the water tells you the volume of your sample. Are we good so far with those concepts? Density is mass divided by volume. There's many different flavors of units, and volume by displacement. Okay, great. So let's do the actual problem. The density of green jade is 3.33 grams per centimeter cubed. And that should be written as a subscript. Okay. A sample of green jade placed in water causes a displacement of 8 milliliters. What is the mass of the sample? So the question is asking about the mass of the sample. And because we know we're dealing with green jade, which is a solid, and we're talking about density, mass is always going to be in grams. So we want to know how many grams is our sample. What do we know? We know that the density is 3.33 grams for every centimeter cubed. You can write a 1 there. It's the same thing. That looks an awful lot like a unit factor. Densities can be used as unit factors just like percentages can be. And that means that you can flip this and say 1 centimeter cubed over 3.33 grams. Okay? So that's how you can use density to solve a problem. You can write it as a unit factor. So to solve this problem, we need to figure out the number of grams. Okay? We're told a displacement of 8 milliliters. We can rewrite that as 8 centimeters cubed. It's all the same. Centimeters cubed and milliliters. If we're looking for grams as our answer, that means that we're going to have to use the unit factor that has grams in the top. So we're going to start off with our 8 centimeters cubed, which is the volume, and multiply by our unit factor. In words, what we're doing is taking a volume and multiplying by mass over volume. When you cancel those out, you're left with the mass. I know we're moving a little bit fast here, but hopefully these are a little bit easier to grasp. So is everyone with me? Density as a unit factor, and how we can set up the problem taking the volume that we know about our sample and multiplying by density as a unit factor. It's the same idea, getting rid of the units and figuring out which units need to be in the bottom, which ones need to be in the top. So all of that we did in the beginning was figuring out which unit factor to use. we're still using that. When you put that into your calculator, you're going to do 8 times 3.33, and your calculator is going to tell you something like this. But we know better. Now, if we did the subtraction like it shows here, we should actually have 8.0 milliliters, which has 2 sig figs, okay? So we're going to go with 2 sig figs for our answer. That means we need to round this 6, and we're looking at the 6 next to it to figure out if we round up or we just drop everything. In this case, we're going to round up. And with 2 sig figs, we have 27 grams. So that's the mass of the sample that displaced 8 milliliters of water. You will have something like that on the exam, where you're going to have to combine. So we did volume by displacement with the water here. There's the other concept of the gas as well that I talked about in the video. So make sure that you're familiar with both of these volume by displacement methods for a solid and for a gas. The last topic that we're going to hit on is specific heat. So specific heat, we're talking about how much energy it takes to raise 1 gram of the sample by 1 degree Celsius. And this is the equation. Q is the heat in joules, which is energy. M is the mass in grams. And delta T is the change in temperature. The temperatures have to be in either degrees Celsius or Kelvin. Doesn't work any other way. Fahrenheit, you're going to have to change to Celsius in order to use this equation. This equation is built on using one of these 2 units, okay? So I wanted to point that out to you to make sure you don't get got. If we're doing a problem, you see this is a big old paragraph, okay? We're going to pick through it a little bit and run through it a little bit quick because we've only got a few minutes left in class. But I wanted to make sure to throw something like this up here so that you see it in action, okay? So you're performing an experiment or reaction in a flask and water. During the course of the reaction, heat moves from the flask to the water bath. The initial temperature of the water bath was 27 degrees Fahrenheit. Final temperature, 45. Then you get the information about the size of the water bath and the specific heat of water. And we're supposed to calculate the amount of heat released into the water. So I kind of have all the things from the problem on this slide. These are our temperatures, we've got our mass, and our specific heat. Remember, I told you you have to convert to degrees Celsius, and that's what this top equation is for. So we didn't specifically go over the temperature conversions because I figured that was something that was easy enough where you just say, okay, I'm trying to go from Celsius to Fahrenheit. I choose the right equation. I plug in the number. Okay. So I'm going to rely on you to practice that and make sure you're good on that. And if you want to do this problem as practice, you can do that and make sure that you get the conversion from Fahrenheit to Celsius. So you have to do that first. Then you calculate delta T. Okay. Once you do that, you can plug everything in and you just rearrange the equation. And I'll show you how to do that. What we need to isolate is Q. That's our heat. Okay, that's why I circled it with red. Hot. To do that, we need to get the mass and the delta T on the other side. Since we have division here, we're going to multiply by m delta T on both sides. So when you're doing this problem, the specific heat of water times the mass of the water times the change in temperature of the water should give you the amount of heat. And I'll go through and give you some of the answers so that you can still kind of go through and do it yourself. So when you're doing the temperature conversions, your initial temperature, you're going to do 27 minus 32, and then take that, multiply by 100, divide by 180. I know that looks like a weird number, but yes, that's a temperature. You're going to do similar things for converting the final temperature, only this time 45 minus 32 is a positive number. Multiply by 100, divide by 180. Notice how I'm putting a lot of digits at the end, okay? We're not doing any kind of rounding right now. We're going to save all of that for the end. Your delta T, you're going to take the final minus the initial. And since we're talking about subtracting a negative number, we're actually going to end up adding. So you should get about 10 degrees Celsius for your delta T. So that's what you should end up doing to get an answer. Now I know that was fast, but to quickly recap, we had to convert the temperatures to Celsius before we calculated delta T. Then we rearranged the equation so that we can solve for heat, which is Q. You figure out your delta T, you substitute in all the numbers, and then you do your math. It should be a big number. And always, always, always sig figs, okay? I'm not going to try to get you too much here, but we've only got 2 sig figs in our temperatures, so you should report your answer as having 2 significant figures. The easiest way to do that is using scientific notation. So if we put a decimal point here, we went 1, 2, 3, 4, 5 decimal places. And that would be your answer. So I'm not going to have anything too complicated on your exam about specific heat. But you will need to recognize this equation and be able to rearrange it a little bit to solve for Q or maybe specific heat. I give you all the information for this, and you have to tell me what the specific heat is of the substance. So if you have questions on that, you can let me know. We've only got a few more minutes left in class. But if you're like, help, that's fine. We can talk about it a little bit in the next class because I know we went through it really quickly. So let me know if you're good or if it's a help. Okay. Yeah, we went through that kind of fast. So what I would recommend doing, rewatch the video and try to do the problem. I've posted, so let me go to my reminders. Okay. So in addition to homework and the exam, I posted a practice test for, so we need to figure out office hours. So everyone needs to do that practice test that I posted over the weekend. It's 3 questions. It's not testing your knowledge of chemistry, but you need to use the Respond as Lockdown browser and monitor. So for scientific notation, I will tell you to report your answer in scientific notation. If you need to report a certain number of sig figs, like in the number that we had before, then you have to use scientific notation. But I won't leave it up to you to decide. I'll tell you which one. So I'll put up, for those of you who have not had to use it because this is your first year, you won't know how to get to Respond as Lockdown browser and monitor. So I'll throw it up onto the Blackboard how you can do that. So I'll make a folder for it. There's a PDF and it's got details on how to do it. So I'll throw that up there and let you know that it's there. Once you get the lockdown browser, do that practice because it's going to, I just want to know what year you are, what your intended major is, and then whether or not you have to take another chemistry course after this or if you're done. And the other question is, I gave you some options for office hours, and I want you to tell me which option works the best. So I've done that for all of my classes. And what you're doing right now is absolutely what you need to do. Form a study group. Help each other. Because it's a lot of material, and some people are going to get some things versus others. So I absolutely encourage it. Study together. And you can do homework together too. Just make sure that when you're writing out your answers to submit, that you're writing your own work. I don't want to see 12 copies of the same thing where everybody gets the same one thing wrong. Okay? So make sure you're writing it yourself, that you're not just taking one document and spreading it. But rewatch the video for the specific heat, and then we'll touch on it again. I am kind of hoping that y'all choose Wednesday for office hours. I have Wednesday pretty much open. So if you guys want to do Wednesday either from 11 to 1 or 2 to 4, those are the 2 blocks that I have for Wednesdays at office hours. So even right now in this class, if you can let me know, Wednesday, do you have time between 11 and 1, or do you have time between 2 and 4? If nothing works for you there, I'm sorry. But we can do that this week at the very least until everyone has done the little practice exam. Yeah, so let me know. So I got 2 votes for 11 to 1. 11 to 1 or 2 to 4. Those are the options for Wednesday. Okay. So of course it's a split. So we can do So then let's do this Wednesday only. Let's do no. Can we say maybe even 12 to like 2:30 to get some of those folks? Okay. So I will put a link on Blackboard and an announcement to let you know where to go for office hours. So anytime from 12 to 2:30 p.m. on Wednesday, that's September 2nd, you can hop on in and ask questions or say, hey, can we do this kind of practice problem? And then we can work it out.